Okay, welcome back. Hope you all had a good weekend. Um, Let me bring up my slides. All right, here we go. Okay, we've been looking at design patterns, and I want to give you two more today, and that will be all the design patterns that we'll be covering. As I said, there are probably, there are several more, and you're welcome to continue looking at the other ones and even make use of some of the other ones if they fit with your project. As I said in earlier semesters, there's the bridge design pattern that a number of students decided to use. So you may want to take a look at that one, okay? All right, so today I want to look at, well, we'll start out with the iterator. It's a relatively easy pattern to understand, but I'll point out that the iterator from the standard template library does not implement this pattern. So let me first show you the pattern, and then I'll show you how the standard template library does iterators. Okay. All right, so the iterator design pattern, the whole idea is that you have some data structure as a container, okay, like a vector or an array or a linked list, okay, and you want to be able to access the elements sequentially. So if it's a vector, you want to go from the first element all the way through to the last element, okay, um, you want to be able to do this for any container. And what the iterator will allow you to do is to iterate over the elements without knowing how the container is implemented. So if you have an iterator, it won't matter if the container is an array or a vector or a linked list or even a hash table. Okay, so that will make your program more flexible because you can change the container and keep the iterator. Okay? This is also an instance of using the principle of least knowledge. Okay? You don't have to know how the container holds the elements. All you care about is being able to go through the elements from start to end, okay, in the order that the elements are in the container. Okay. All right, so the iterator then knows how to access the elements of the container, okay, and that information is hidden from you. You don't have to know that. Okay, all you have to know is how to work with the iterator. Okay, so to make this work, then all the iterators are subclasses of an iterator superclass. Okay, and therefore using polymorphism and coding to the interface, your code will be able to work with an iterator that knows about different containers. Okay, and the iterator then internally will maintain what's known as a cursor to keep track of where in the container it is. So, the cursor starts out, at the first element. Then you can move the cursor to the next element and so forth. And the cursor or the iterator will know how to move that cursor. Okay, and all your code has to do is say, okay, I want the next element. I want the next element and so forth until you reach the end. Okay. All right. So here are common member functions of iterator. Okay. So these are member functions that will be pure virtual functions of this iterator subclass. Okay. A function first returns the first element of the container. Okay, so if it's a vector, you'll get back the vector sub 0. If it's a linked list, you'll get back the element that's at the head of the linked list. Okay. Current item then returns the current element. So wherever the cursor is, let's say that it's a vector and the cursor of the iterator is currently at the fourth element. Then when you call current element on the iterator, you'll get back the fourth element. Okay. Next says, okay, move the cursor to the next element. Okay, so if the current element was the fourth element and you call next on the iterator, then the iterator moves to the fifth element. Okay, and is done returns true or false depending on whether the cursor has reached the end of the container. Okay, so with these 4 member functions, you should be able to iterate over any container that maintains its elements in some sequence. Okay, I mean, the iterator goes from first to last, so that the assumption is that there is some sequence in the way the elements are stored. Okay, even if you use the a hash table, okay, quite often a hash table is maintained so that the elements in the hash table are sorted by their keys. Okay, so even though the way you access an element of a hash table is by using the key, internally the elements are maintained in sorted order by the keys, and so you can use an iterator on a hash table. Okay, so any container that maintains its elements in some order can have an iterator. Okay, all right, so let's take a look at how we would implement an iterator using the iterator design pattern. So here's the superclass called iterator, and you can see that it has first, next, current item, and is done, just as I showed you earlier. And each one of them is a pure virtual function. In other words, each one of these is an abstract function, which means that we have to have iterator subclasses that actually implement these functions. So let's take a look at one of them. Okay, so here is an array iterator. Okay, and so this is an iterator designed to work with an array. Okay, so here I'm going to, construct an array iterator. I give it the array that I want to iterate over and the size of the array. Okay, and there is some private members here for the array and its size. Okay, and then here's the cursor. Okay, and we initialize the cursor to 0 so that the cursor is at the beginning of the array. Okay, well, then these functions are really easy to implement. The function first then returns the first element of the array. Next says, okay, return the next element of the array. And so, of course, we increment cursor by 1 and return the value of the array at the new cursor position. Current item says, okay, just return the array element at the current cursor position, and is done, test whether or not the cursor has reached the end of the array. Okay, so there's our iterator for an array. Okay, now we can have an iterator for a vector, and it's going to look very similar to the iterator for the array, except that we don't have to pass in the size of the vector, whereas for the array, so we passed in the size. But vector, we can get the size by calling the size function on the vector. And so here's first, next, and current item, and is done. Check to see if the cursor has reached the end of the vector. Okay. So here we have 2 iterators. These two happen to look very similar. There's one for an array and one for a vector. So let's see how we can make use of this. Okay, so here I've created an array, Okay, so it has 10, 20, 30, 40, and 50 in it. Okay. Here I've got a vector, and I'm going to put 100, 200, and 300 into the vector. Okay. All right, so here is the array iterator, which I'll call AIT for array iterator. I pass in the array that I want to iterate over and the size of the array. And here's the vector iterator. All I have to do is pass in the vector. Okay. Now remember, array iterator and vector iterator are both subclasses of the iterator superclass. Okay. All right, well, you can see here I'm passing the array iterator to my print function. And here I'm passing the vector iterator to the same print function. And of course, the print function then uses coding to the interface. So IT, the parameter, is of type iterator. Okay, and therefore I can get the first element. Okay, I can iterate over all the elements by calling next. Okay, and then checking to see if I'm done. And so the first time I call print, I'm passing in the array iterator, and sure enough, I get the array values printed out. And the second time I call print, I'm passing in the vector iterator, and there are the vectors elements. Okay? So this print function can handle any iterator. Okay? I can pass in an iterator for a linked list, an iterator for a hash table, whatever, as long as the iterator is a subclass of the iterator superclass. Okay? So this is the power of iterator. So if you're given a data structure and you don't want to know how the data structure is actually implemented, yes, such as a hash table. Okay? You don't want to know how the hash table actually stores its elements. But if you're given an iterator for that data structure, then you'll be able to iterate over the elements of that data structure without knowing anything at all about how that data structure was implemented. And in fact, you don't even know how the iterator is implemented, other than the fact that it has these four functions. Okay. And so here is the implementation of the four functions for a vector, and it was very similar for an array in this case. But see, using the principle of least knowledge, you don't have to know anything about the container other than the fact that somehow it stores all its elements in some sequence. And you don't have to know anything about how the iterator knows how to access the container's elements. All you have to know about the iterator is that it has these four functions. Okay? So that is basically the iterator design pattern. Okay, so let's okay, there's the example. Okay, and here's the design pattern. Okay, so aggregate is what I've been calling the container. It's the thing that holds on to the elements. Okay, and now the way the design pattern works, and I didn't actually do it in my example, is that the part of the design pattern is that the aggregate has a, I guess you could call it a factory function that creates an iterator. Okay, so if I had done things completely the way the design pattern says in my examples, the vector container would have had a member function that creates the vector iterator, whereas I actually created it separately by creating this class. Now, if you were given a container and you didn't know anything about the container, but you can call the make iterator member function of that container, and it would return an iterator for you. And then, of course, given that iterator, you'd have these four functions to call. So that's actually the complete design pattern here. Okay, so once again, here is our aggregate, our container data structure. It has a create iterator member function. So both of these are shown as abstract because we would have a concrete aggregate. So you would have a vector aggregate or an array or a linked list aggregate. And each one of those aggregate subclasses would then implement create iterator, and it would return the appropriate iterator for that container subclass. Okay. All right, so here's our client, the program that makes use of the aggregate. And here from the concrete aggregate, we're going to get a concrete iterator. Okay. Now the client knows only about the only knows that the aggregate allows you to create an iterator. And as far as the iterator is concerned, all the client knows is that the iterator has these 4 functions. So now that means that the client will be able to access in order the elements of the container without knowing anything about the container other than it has create iterator function, and without knowing anything about the iterator other than it has these 4 functions. Okay, so that is the iterator design pattern. And so the next time you design a data structure, you create some class that will contain some data, and this data structure, this class that you've created, maintains the elements in some order. That doesn't mean that the elements are sorted in any way. The only thing is that they are in some sort of sequence, meaning that there's a first one, and for each element there's the next one, and then obviously there has to be a last one. Then if you create this class, this container class, you should also create an iterator for that class and have this create iterator function so that whoever uses objects instantiated from your container class can then create an iterator, and then that iterator should be able to iterate over the elements of your container class. Okay, so you would write the code for a concrete iterator, a concrete aggregate, that's a container, and then you would also have to write the code for its iterator. Okay? And then any code that makes use of your container only needs to know that that code can create an iterator, and then use that iterator to access the elements of your container. Okay, so that's the beauty of the iterator design pattern, in that it hides so much implementation detail from you, and you're given interfaces to allow you to do your work. So you can create an iterator, and given the iterator, you can use the iterator to access the elements of this container. Okay, any questions about this design pattern? This design pattern is extremely useful if you have an application that has, well, you created a new container and you want to hide the implementation details because you may decide later on to refactor that code, etc. And so if you don't expose your implementation, then you don't have to worry about causing other people to have to make changes to their code when you change the implementation, because all that the other code is going to be using will be your iterator. And as long as you maintain these 4 functions, okay, you can do whatever you want as long as those 4 functions are still there. Okay. All right. Any questions? Okay. Yeah. Now, let me compare what I just showed you with what the standard template library provides. And I'm sure you've learned about C++ iterators. Now, C++ iterators, the ones you get from the standard template library, do not follow the iterator design pattern. Okay, and so this is a good opportunity to see what the advantages are of using the iterator design pattern, and then you also see what the disadvantages are of not using the iterator design pattern. Okay, so we'll take a look at how the standard template library implements iterators. Okay, now there's no iterator superclass. Right, you saw how important it was for the iterator design pattern to have that iterator superclass. Well, there is no iterator superclass from the standard template library. Each container type has its own iterator type. Okay, well, you know, what I showed you earlier, yeah, the array had its own iterator and a vector has its own iterator, but both the iterators were subclasses of a superclass. Okay, given that the STL does not have an iterator superclass, that means truly each container has its own iterator type. Okay. And the way the STL does iterators is that an iterator actually behaves very much like a pointer variable. Okay. All right, so let's take a look at how we would do this with the standard template library. Okay, I've replaced array with linked list because a linked list comes from the standard template library along with vector. Okay, so here's my linked list. Here's my vector. Okay, so I've initialized the linked list to these values. So this is the head of the list, 10, and the tail of the list is 50. Okay, and when I initialize this list, the list is automatically linked up with forward and back pointers, so you don't have to worry about that. And then of course the vector is the vector. Okay, now here I am. It's a LIT for list iterator is the data type. And notice you take the data type of the container, which is list of integers, and then it's : iterator. Okay, so that is the iterator data type associated with this linked list of integers. Okay, and VIT, vector iterator, this is the iterator associated with a vector of integers. Okay, so again, it's vector of int : iterator. Okay. All right, now, just as before, I want to print out the elements of the linked list and the elements of the vector using the iterator. Okay. All right, well, I'm going to initialize the iterator to the start of the linked list. Okay, so every container then will have a begin member function that returns the start of the elements. Okay, and it has an end, which is actually not the last element, but it's a pointer to one past the last element. Okay, so you have to keep that in mind. All right, so I'm calling my print function. Okay, and notice I'm passing in the list iterator. Okay, and then I'm also passing in the end of the list. Okay, here for the vector, I'm calling the print function, passing in the vector iterator and the end of this particular vector. Okay, now LIT and VIT are two different data types, right? A VIT is a list iterator. LIT is a list iterator and a VIT is a vector iterator. So guess what? I need two functions. So this is the print function for a list iterator. Now notice here, excuse me, when I call it, I'm passing in the iterator that I created, okay, and I'm passing that in by reference, okay. So IT parameter is a list iterator, an iterator for a list of integers, and then I'm also passing in the end of the list, okay, and I'm passing that in as a constant, okay. So end is a pointer to one past the end of the list, okay. All right, now I can iterate, okay. So as long as the iterator is not pointing to the end of the list, okay, I can then print out the what the iterator is currently pointing to, and so I dereference the iterator. Okay, I said earlier that iterators coming out of the standard template libraries behave like pointers. Okay, so whereas in the iterator that we had defined earlier, that's part of the iterator design pattern, we had a cursor that kept track of where we are in the container, because an iterator here behaves like a pointer. Well, we just dereference it, and then to move it to the next one, we increment the pointer. We increment the iterator, okay? And so this is how we would iterate over the contents of the list, okay? We've already initialized the iterator, okay, when we first passed, before we passed it, and then we also pass in a pointer to the end of the list, okay? Remember, it's actually a pointer one past the end of the list, okay? And so here, first come in, IT is already pointing at the beginning of the list. We dereference it to print out that element. We increment the pointer or increment the iterator to point to the next element. And we keep doing this until the iterator is now equal to end, which we had passed as the end of the list. Okay. Okay, and we do the same thing with the vector. Okay, so same thing here. Okay, but we have to have another print function because this is a different data type. Okay, and otherwise the code is the same. Okay, so if we had more containers coming from the standard template library, okay, we would have to have a separate print function for each one of them. Okay, again, because there is no iterator superclass, so we cannot use coding to the interface. Okay, okay. And data structures coming out of the standard template library, like list and vector, map, set, and so forth, you will be able to create an iterator from that class. So this notation here is basically for the design pattern is this create iterator, okay? Except it's not a function. You actually declare this iterator data type, okay? Using the data type of the container, and then using scope resolution, you then, using the scope operator, you then say, I want an iterator for this container, okay? And so this in effect is creating the iterator for us, okay? All right, so hopefully you'll now appreciate the differences between iterator from the point of view of the iterator design pattern, and iterators from the point of view of the standard template library. Okay, I would venture to say that the design pattern iterators are much more flexible. Okay, I don't know why they didn't make an iterator superclass, but they did not. So this is what we have to live with. Okay. All right. Any questions about iterators? Okay. Not a very difficult concept, But when you're designing your code, you have to decide whether you want to implement the iterator from the design pattern, or if you just want to use the iterator that the standard template library provides. And that's a decision, a design decision that you make depending on your application. I mean, if you want to have a generic print function that works with any iterator, then you want to use the design pattern, because here you can see that iterator is the superclass, and using polymorphism and coding the interface, we just have to write one print function that will work with any container. Okay, but then this is a bit of work that you have to actually create the iterator class. Okay. Now, whereas if you use standard template library, iterators are already built in. Okay. However, here in this case, to do the print function, you're going to have a separate print function for each for each and every iterator type. Okay, so you're basically here, you're overloading print. Okay, with a different parameter type. Okay. Okay. Any questions about this one? Okay. Okay, let me show you the last design pattern that I want to cover, and it's another extremely useful one. It's going to remind you of the decorator in many ways. Okay, now the composite design pattern, as its name implies, you're putting some things together. Okay, just like with the decorator, you remember decorator, you're wrapping objects with the various decorators. Here, you're not necessarily wrapping, but you are composing, and this is a design pattern to help you compose objects. Okay. All right. So let's say you have a tree structure. Okay, that's a very typical way of composing objects is to put them into a tree. And now a tree represents this whole part hierarchy, right? The entire tree would be a whole, and any subclass or any subtree would be a part. Okay, so a tree maintains this hierarchy of parts. Okay. So my example is that, okay, a university has schools, each school has departments, each department has courses, each course has teams of students, etc. Okay, so there's a hierarchy here. Okay. Now, the whole idea behind this design pattern is that in your application, you want to treat an individual object and compositions of objects uniformly. So whether it's an individual object or a composition of objects, you want to treat them the same way. Okay, and if you think back to the decorator design pattern, it was you wanted to treat a beverage object the same way as you would treat an object that was wrapped in mocha and whipped cream and whatever. And whether it was a decorated object or an undecorated object, you treated them the same way. Okay. Similarly, here in the composite design pattern, okay, you would treat an individual object the same way as you would treat a composition of the objects. Okay, so since we're talking about trees, you would treat a single node object the same way as you would treat a subtree. Okay, so that's the idea behind composition. Okay, all right. So here is a tree here. Okay, we have a science, and science is made up of physics, biology, and chemistry. Physics is itself is made up of classic and quantum, and then if you keep drilling down, you'll see that there are names. So quantum has, I guess, Tom and Jane working in in quantum physics, and biology has Dick working in biology, okay? And so the red here is the entire tree, okay? Now, green here is a subtree, okay? We're only looking at quantum, okay? And purple here is a single node, a leaf element. So we're just looking at Jane, okay? So here we have the entire tree, a subtree or one group, okay? And we have a single node or one person here, okay? Now the idea, again, with this design pattern is that we should be able to treat an entire tree the same way as we would treat a subtree, the same way as we would treat a single node. Okay? That's the composite design pattern, okay? All right, so in order to make that happen then, of course, we have to have a superclass, okay? And we're going to call that component, okay? So a single node, okay, or a subtree, or the entire tree, each one of them will have to implement component in order for us to treat them all the same way, okay? All right, so here we have component, and let's say that it has a print function so that we can print out that component, has an add function so we can add a child component to any particular component. And okay, here's a function that does indentation when we print, okay? All right, so then and then each component has a name, okay? So there we go. So this is the superclass component, okay? Now a person, okay, is going to be a component, okay? So a person then being Tom, Jane, or Dick, okay? So we have to implement the print function. Let's see what we have here. So yeah, print and add are virtual functions here. Okay, they're both abstract, they're both pure virtual functions. And so we have to, be able to print a person. So we just, do an indentation and then print. Okay, so, and then adding, well, according to the way we designed the tree, it doesn't make sense for a person node to have children nodes. And so the add function basically doesn't do anything, okay? So again, if you look at our tree, the person nodes are designed to be the leaf nodes. And so we won't be able to add children to each of the person nodes. And so add is basically a no-op here, okay? Okay, well, then group then, okay, remember group then is like a quantum. So a group then will have persons in it, okay? Well, a group, okay, well, it is a subclass of component, okay? It has a print, okay? Now, when we print a group, we print its name, and then we have to print its children, okay? So here we're going to iterate over the children, and then you can see that group has a vector of children, okay? And then so here it does make sense to add a node to a group, and so here we're basically passed in a child. Notice that child is a component. We're going to just append it to the end of our children vector. Okay. All right, so this is group, okay? And let's take a look. Okay, so here is our main program. Okay, let's see, we're going to create 3 groups. Okay, there's a science group, physics group, biology, and chemistry. Okay, remember here's physics, biology, chemistry. Oh, and then of course there's the group science itself. And so we have 4 groups here: science, physics, biology, and chemistry. Okay. Now we're also going to create a classic and quantum groups. Okay. And then here are the persons. Okay. Now we're going to start doing the compositions here. Okay, so to science, the group, we're adding physics, biology, and chemistry. Okay, so now we have the children of science. Okay, and then to quantum, we're going to add Tom and Jane, and to biology, we're going to add Dick. Okay, so now we have built our tree. Okay, so we're going to call the print function. Okay, on each one. Okay, and we can print out the entire tree. Okay, and that will give us the entire tree. Okay, or we can print just one group. So we're just going to print quantum, and then we'll end up getting quantum. Or we can just print out one person, and that will just be Jane in this in this example. Okay, so what have we done? We have this composition, and we're able to treat any level of the composition the same way. Okay, we can print each person, we can print each group, or we can print the entire tree. Okay, and so that basically is the composition design pattern. Okay, and again, the way this works out is because person and group are both subclasses of component. Okay, and so here you can see lots and lots of uses of programming to the interface. See, we can assign group objects to a component. We can assign person objects to a component, and then when we're done building this giant composition, we can then treat each level of the composition the same way. Okay? Just as we had earlier treated a beverage the same way as we treated a wrapped beverage, because the wrapper and the beverage both were subclasses of the same superclass. Okay, here our superclass is component. Okay. All right, so that is a composite, and so here you can see here that here's a client. Okay, that's our test program, and here is the component, and you can see that there's some operation we can perform on components. In our case, that was print. We can add to a component. Okay, I didn't show you removing a component, a child component, or getting a particular child. Okay, all I showed you was basically add and print. Okay, and here we can have a leaf node. Okay, and it is a subclass of component, and you can perform the operation on the leaf node, namely print. And here is a composite. Okay, now a composite is like our group. Okay, a composite can have children. Okay, but you can also apply the operation on the composite, and that's because a composite is also a subclass of component. Okay. All right, so this is the composite design pattern, and it's applicable whenever you have some data structure that reflects this whole and part hierarchy. Okay, the whole tree or part of a tree, namely a group or a subtree, or even down to a leaf node. Okay. Everybody is going to be a subclass of component. That allows you to treat all levels of this hierarchy the same way. Okay. All right. Any questions about composite? Okay. Also extremely useful. Okay. Well, all these design patterns are useful. And out of the 23 in the original Gang of 4, I think I've given you about half of them. Okay. The ones that I find the most useful. Okay. All right. So given that I've shown you well, exactly how many of these patterns I've given you. This is 1, 2, 3, 4, 5, 6, 7, 8. I'll give you 9 patterns. You should be able to recognize in your projects which patterns you're going to use and how. Okay, so your next assignment is not necessarily coding, but just a brief report that says, okay, in your project, you know, the one you're all working on, can you find 3 design patterns? Okay, and then once you've identified the patterns for each one, say, how did you implement that pattern? Okay, now I've shown you the UML diagrams for each of the patterns. Well, then draw a UML diagram of, you know, from your design of your project and show how your UML diagram relates to the design patterns UML diagram. And you've seen examples of this over the past couple of weeks, where I've shown you UML diagram from the example code, and then I showed you the generic UML diagram for a design pattern, and then you can see the relationships between the two of them. Okay. Now, because I'm assuming that you've all started on your projects, but even if you haven't, then propose how you would use a design pattern. I mean, at the very least, this is going to make you start thinking about your project, because I'm going to say, all right, in the design of your project, even though it may still be very sketchy, what are 3 design patterns? Okay. Okay, so this is definitely not correct. I'm going to have to give you the correct due date. Okay. Now, let's talk about your project presentations. Now, you're a very small class, so there's only 2 teams, and so no problems fitting 2 presentations in the same day. You know, I said max 20 minutes. If you want to take up to half an hour, that's fine. If it only takes you 10 minutes, that's okay too. But remember, it has to be GUI based. So you're going to use WX widgets. If there's another graphics package you want to use instead, okay, that's fine too, as long as it's C++. Okay. Now, what we're going to look for is your use of design principles and design patterns. Right? That's the whole purpose of this class, was to get you to write well-designed programs. And so we fully expect that your project code will be well-designed. Okay, and then give us a demo of of your application in action. Okay, and I left it pretty open-ended what this application could be. And so as long as it's GUI based and you make sure that you design it well. Okay. Now, when each team is doing its presentation, the rest of the class will be evaluating the presentation. So there will be a survey available in Canvas. And so each presentation will be ranked according to certain criteria. Okay, and here are the survey questions. Okay, so you're going to judge how well did the team describe this application, how well did the team present the design of the architecture. Okay, so I expect UML diagrams and things like that. And then how well did the team describe design principles and design patterns that the team used. Okay, and then how well did the demo go? And at the end, we want to have some Q&A. Well, how well did the team respond to Q&A? And so there, I'm going to have a survey of these questions, and each survey, you'll be able to check, poor, okay, good, or excellent. Okay, so you'll be able to rank the presentation for each of these questions. Okay, and at the end of the semester, when I grade the projects, part of the grade will be based on how well you did with your presentation, how well you orally describe your design. Okay, and then your report. Okay, well, the report will be, a lot of it will be based on your next assignment, which is to describe 3 design patterns. Okay, so now you have a chance of describing your finished code and saying, well, here is how we use the various design patterns. But basically, the report is a write-up of your oral presentation. Okay, you basically need to describe the same things. Okay, you turn in the report, your slides, from your oral presentation. Turn in the code of your application, because the grader and I are going to want to try running your application. Okay, and this will be due Monday, the 17th, which is the last day of the semester before final exams. Okay, right. So that will be your final semester project, and basically, show us what you learned. Okay, hopefully, in any future software project, you will be a better software designer. Okay. Okay. Any questions at all about this project? Okay, and the presentation. Now, as I said earlier, what I want to do for the rest of the semester is to go over some of the newer features of C++. I mean, it's great to learn about design principles and design patterns, but presumably you're going to be implementing these principles and patterns in an application that you're going to write in C++. And it turns out that C++ does have a number of new features in, let's see, I currently mostly use the 2011 version of C++. There's a 2014 version, a 2017 version, and I believe a 2021 version is coming out. And so they keep adding more and more features to C++, as if that language isn't complicated enough as it is. So I want to point out some of the major ones that will help you to write programs that are better designed and maybe even easier to read. Okay, and there's one or two features that will enable you to have your code run more efficiently. So not only will it be well designed, but it will perform better. Okay, so there are a number of things that I can point out. C++ being a very, very complicated language. I mean, they've thrown everything into that language that they can think of, and they keep adding new features to it. You know the old saying about power tools. Power tools enable you to build things very quickly, but if you don't use the power tools correctly, you could saw off your fingers. So C++ is like that. When I teach the CompE 180A, which is the graduate C++ class, I go over a number of pitfalls of the language, things that, if you're not careful, you're going to cause your program to go haywire and, crashing, performance, perform very badly. And, so unless you know to avoid these pitfalls, you can get yourself into a lot of trouble. Even if your program is beautifully designed with design principles and design patterns, if you do not use the C++ language well, you're still going to get into trouble. So I want to spend a couple of weeks going over some of these new features and pitfalls of C++. Okay. Any other questions? Any issues that you want to discuss with me? Okay, looks like we're going to end the class a little bit early today. Otherwise, okay. I will again have my office hour at 4:30. Oh, before I forget, this morning I got word of another internship at NASA Ames, so I'm going to have to post that, and I will then send out an announcement to all of you, because you're my students. I want to give you first dibs at these positions. So keep an eye open for that. That should happen later today. I just got the write-up from NASA, and I confirmed with them that it's open to anybody. You do not have to be a U.S. citizen or a permanent resident. So international students can apply. And this position has to do with natural language processing in Python. And what a coincidence. Last Thursday night in my data science class, I went over the natural language toolkit of Python. And so here we go. We have a internship basically to analyze text and going over NASA documentation and so forth. And I briefly looked at the job posting, but I suspect it has to do with being able to classify and index documents based on their content. So if you're at all interested in natural language processing, especially if you're familiar with the Python toolkit for doing natural language processing, then you really want to consider applying for this position. Okay? For undergrads, we're paying, I think, around $23.50 or around there an hour. So it's definitely not a bad job to get. It's above minimum wage for sure, and you get to work with NASA. Now, initially, it'll be remotely because NASA is locked down like everybody else. We're hoping that by the end of the summer, it depends on Santa Clara County and everything. We hope that by the end of the summer, the lockdown will be over, and then you'll actually be able to work on the NASA Ames campus, and that is super cool. Okay, believe me. Okay. Any questions? Any comments? I guess you all know that they managed to fly that helicopter on Mars. They successfully had the helicopter lift off. It flew for about 30 seconds and then landed again. That was the first flight. And it's basically a demo, proof of concept that, yes, indeed, we can fly drones on other planets. And I think we can foresee that in the not too distant future, we're going to have a swarm of helicopters buzzing over Mars. And of course, a helicopter can travel a lot farther than a rover can. And so this could be a real win. They're also talking about a helicopter or drone flying on Titan, one of the moons of Saturn. And you know that NASA has already landed a lander on Saturn. That this happened, gosh, quite a while ago, maybe 15 years ago. And so now they're talking about having a drone flying around on the moon of Saturn. So this is really exciting that we're able to do this. Okay? So that's why you really want to consider these internships at NASA. Okay, well, that's enough of me blabbing. So any other comments or questions? Okay, if not, then I will shut everything down. Okay. All right. Thank you for coming.